Hello, welcome to the course SJPHY2C02 Optics, Laser and Electronics. The contents of today's lecture is taken from Principles of Electronics by V.K. Mehta. We will continue to discuss topics from Module 4, Electronics. In the last two classes, we had an overview about the basics of semiconductor physics, where we discussed in detail about the formation of a p-n junction diode. In today's class, let's discuss about some of the applications of a crystal diode. First one is a diode rectifier. Rectifier is a circuit, an electronic circuit which converts AC signal into DC. So if you look into your house, the power supply which comes into your household is an AC supply, but many of the appliances which you use requires DC power supply. For example, television, computer, your mobile phone, or even the LED lights. All these require DC power supply. So there is a requirement to convert AC signal into DC. And this is where a diode rectifier comes into picture. There are two types of rectifiers, a half-wave rectifier and a full-wave rectifier. First, let's talk about half-wave rectifier. So usually for a rectifier, the AC supply is given through a transformer because it's easy to step up and step down voltage using a transformer. I hope you know the working principle of a transformer. So it has a primary coil and a secondary coil, and depending on the turn ratio, you can either step up or amplify the signal or step down the signal strength. So typically when the number of turns in the secondary coil is greater than that of the primary coil, then you can amplify the signal. If the secondary coil turns is less than that of the primary coil, then you step down the signal. Okay. And secondly, as you can see, there is no electrical contact between the primary and secondary coils of a transformer. Okay, so in this way you can isolate the rectifier circuit from the power lines, thereby reducing the risk of electrical shock or electrical damage. And this is the circuit diagram of a half-wave rectifier. So the secondary coil of a transformer, it is connected to a p-n junction diode. Then you have a load resistor RL. Load is anything across which you draw your output signal. It could be a simple resistor or it could be a circuit as such. Okay. So you can see the secondary terminal has two leads A and B. So during the positive half cycle of the input signal, point A is positive and B is negative. So as you can see, this is the P side of the diode and this is the N side of the diode. So when A is positive, B is negative, P side is connected to positive, N side is connected to negative. In other words, the diode is forward biased and it conducts. So you get an output across the load resistor. During the negative half cycle, A is negative, B is positive. Now the P side is connected to negative terminal, N side is connected to positive terminal. In other words, the diode is reverse biased and doesn't conduct. So during the negative half cycle of the input signal, you do not get any signal at the output side. So basically the circuit is going to give you an output only during the positive half cycle, and you can see the current flows through the diode only during the positive half cycle, and it always flows along the same direction. Thus, a pulsating DC output is obtained across the load resistance R. But as you can see, this is not a clean DC, this is a pulsating DC. You can make it a clean DC by using a filter circuit. We will discuss about filter circuit later in this module. Now, what are the disadvantages of this kind of a rectifier circuit? First thing, you are utilizing only half the cycles of the input signal, right? So the output is going to be low. Secondly, if you look at the frequencies of the input and output signal, so what is frequency? It is inverse of the time period. So time period is the time duration after which the signal is going to repeat itself. Okay. So here you can see it starts from 0 degree all the way to 360 degree. Here one full cycle is completed. After this, the wave is going to repeat itself, right? So the time period is from 0 degree to 360 degree. This is the input side. And if you look at the output side, during the positive half cycle, you have now an output, and during the negative half cycle, there is no output. Okay. But after 0 to 360 degree, if you look at the next slot, 360 degree to 720 degree, you are going to get exact replica of this signal. So here also the time period is going to be 0 to 360. After that, the output is going to repeat itself. So the time period is same for input and output. Therefore, the frequency F out is same as the input frequency F in. So since the frequencies are same, you need to have extensive filtering to produce a steady DC. So these are the two minor disadvantages of a half-wave rectifier. But the major problem of a half-wave rectifier is that its efficiency is very low. By the way, what is efficiency? Efficiency is usually defined as output by input. In the case of a rectifier, output is DC and input is AC. So you can define efficiency eta as DC power output divided by AC power input. So let's say V equal to Vm sin theta is the AC voltage that appears across the secondary winding of the transformer. In other words, Vm sin theta is your input AC voltage. Let RF be the internal resistance of the diode, RL be the load resistance, and I be the instantaneous current through the circuit. Now, as I said, the output current is a pulsating direct current, so its magnitude keeps changing. It's difficult for you to measure the instantaneous value of the current. So let's now talk about the average value, which is the measurable power. Okay. So how do you find out the average current? Now, the average current is defined as the area under the curve in one complete cycle divided by the time duration. Okay. So how do you find out area under a curve? You simply integrate the signal, right? So you integrate from 0 to 360 degree, or in terms of radian, 0 to 2 pi signal I multiplied by the angular element d theta divided by one complete cycle is from 0 to 2 pi. So divided by 2 pi. So I average or IDC is defined as 1 over 2 pi integral 0 to 2 pi I d theta. But as you can see at the output side, you have some meaningful current only during the first half of the time period. So you might as well write it as integral 0 to pi I d theta divided by 2 pi, because from pi to 2 pi there is no signal. Now, current is nothing but voltage divided by resistance. Voltage is Vm sin theta. Resistance is a sum of resistance of the diode and the load resistance. So this is going to be Rf plus Rl. So Vm, Rf, Rl, all these are constants. You can take it outside the integral. So I average equal to Vm divided by 2 pi Rf plus Rl integral 0 to pi sin theta d theta. Integral of sin theta is minus cos theta. You apply the limit. Cos pi is minus 1, cos 0 equal to 1. When you apply the limits, you get the term inside the bracket as 2. So your I average is going to be Vm divided by Rf plus Rl into 1 by pi. Now what is this term here? Vm is the maximum voltage, Rf plus Rl is the maximum resistance. So maximum voltage by maximum resistance is the maximum current Im. So now you can write the DC current IDC as I maximum divided by pi. Once you find out the current, now you can find out power. Power is nothing but I square into R. So the DC power output PDC is going to be the output current I square DC multiplied by, you are drawing the output across the load only, so I square DC multiplied by RL, or in terms of Im, this is Im by pi whole square multiplied by RL. And what is the AC power input? Once again, if you look at the input signal, this is a sinusoidal wave. The amplitude keeps changing, so it's quite practically not possible to measure the instantaneous value of the current. So let's talk about the average value once again. So in the case of this kind of a sinusoidal signal, the average value is given by the RMS value, root mean square value. And from your +2 classes, you would have studied that in the case of a half-wave rectifier, the RMS value is given by the maximum value divided by 2. In case you don't know about this result, you can refer to the textbook. I am not going into the details of this derivation. So the AC power, PAC, is going to be IRMS square multiplied by the resistance. So the input signal is given to both the diode as well as the load. So the total resistance is going to be RF plus RL. So PAC is IRMS square into RF plus RL. As I said, IRMS is I maximum divided by 2. So PAC is going to be IM by 2 whole square into RF plus RL. So once you have defined the input and output powers, now you take the ratio of these two, that will give you the efficiency. So that's going to be 0.406 RL divided by RF plus RL. Or if you take RL to the denominator, you can rewrite it as eta equal to 0.406 divided by 1 plus RF plus RL. What is the maximum efficiency possible? For efficiency to be maximum, you need to have the minimum denominator here. That happens when RF is negligible compared to RL. So denominator is going to be 1. So the maximum efficiency is 0.406, or in terms of percentage, you simply multiply this by 100, you get eta maximum equal to 40.6%. So during a half-wave rectification, a maximum of 40.6% of the AC power is converted into DC. So as you can see, this is not a very efficient method because more than half the signal is wasted. What's the reason? Because you are dealing with only the positive half cycle, or only the half of the half cycles here. So obviously you can improve the efficiency if you exploit the negative half cycles as well, and that is the principle behind the working of a full wave rectifier. Now before getting into the details of a full wave rectifier, let's do a couple of simple problems. An AC supply of 230 volt is applied to a half-wave rectifier circuit through a transformer of turn ratio 10:1. Find the output DC voltage as well as the peak inverse voltage. So you would have studied this in your +2 classes, the relation between the turn ratio and the voltage. So the primary voltage divided by secondary voltage equal to the primary turns divided by secondary turns. Okay, that's the simple idea. So here N1 divided by N2, the primary turns divided by secondary turns equal to 10, and the primary AC voltage is given. This is the RMS voltage, right? This is the average value. So from RMS value you can find the maximum value. Hope you know this relation. The maximum value of voltage is given by square root of 2 multiplied by the RMS value. So root 2 multiplied by 230, this is 325.3 volts. So this is your primary maximum. So you know the turn ratio, you know the maximum primary voltage. Now you can calculate the maximum secondary voltage. As I said, primary voltage divided by secondary voltage equal to primary turns divided by secondary terms. So when you rearrange the terms, you get the secondary maximum equal to primary maximum multiplied by N2 by N1. Plug in the values, you get the secondary maximum equal to 32.53 volts. Secondary maximum means this is the input AC voltage into your rectifier circuit. Now as we have derived earlier, IDC equal to IM divided by pi. So once you know the DC current, you can calculate the corresponding DC voltage by multiplying current with the resistance. So VDC equal to Im by pi into RL. And what is Im into RL? One thing you have to remember, we are asked to assume that the diode is ideal. Ideal diode means its internal resistance is 0. So you don't have to bother about RF anymore. So current multiplied by the resistance. This is nothing but the total voltage, right? The total input voltage. So Im into RL is VSM. So VDC equal to VSM divided by pi. And VSM is 32.53. When you divide it with pi, you get the DC voltage as 10.36 volt. Okay, so the first part of the problem is done. Second one, what is a peak inverse voltage? Peak inverse voltage is the voltage that drops across the diode when it is reverse biased. Remember, when an electrical component is not conducting, the entire voltage is going to drop across it, right? So during the reverse bias, the diode is going to act like an open circuit. There is no current flow, so the entire input voltage is going to fall across the diode. So the peak inverse voltage is nothing but the maximum secondary voltage of the transformer, and that is 32.53. So peak inverse voltage is 32.53 volt. Another problem, a half-wave rectifier is used to supply 50 volt DC to a resistive load of 800 ohms. The diode has a resistance of 25 ohm. Calculate AC voltage required. So VDC is given 50 volt, diode resistance RF is 25 ohm, load resistance RL equal to 800 ohm. So if Vm is the maximum value of the input AC voltage, then we know VDC equal to IDC into RL, or in terms of Im, this is Im by pi into RL. And maximum current, Im is nothing but maximum voltage Vm divided by RF plus RL. You plug in the values, 50 equal to Vm divided by pi into 25 plus 800 into 800. From this you get Vm equal to 162 volt. Okay. Moving on to the full wave rectifier. As I said, in the case of half wave rectifier, since we are exploiting only the positive half cycles, the efficiency is pretty low. So in the case of full wave rectifier, it utilizes both the half cycles of the AC signal by using two diodes. So here one diode supplies current to the load during the positive half cycle, and the other one supplies current to the load during the negative half cycle. So you are utilizing both the half cycles. And the current always flows through the load in the same direction, and thus you get a pulsating DC. And this scheme can be implemented in two ways. One is a center tap full wave rectifier, and the second one, which is the most popular one, a bridge rectifier. Let's first talk about a center tap full wave rectifier. So this is the circuit diagram. A center tap transformer has three leads. So you have a positive one here, a negative one here, or a live and neutral, and the middle one you can treat it as the ground. And you have two diodes here, and in between these two you have a load resistor which is connected to the center tapping of the transformer. Now, what happens during the positive half cycle of the input signal? So here you can see that since D1 is connected to the upper half, it's going to, the input voltage of D1 is going to be the voltage across the upper half OA of the transformer. And since D2 is connected to the lower half, the input voltage of D2 is going to be the voltage across the lower half OB. And during the positive half cycle, A is positive and B is negative. Now look at D1. The P side is connected to positive, whereas in the case of D2, the P side is connected to negative. In other words, D1 is forward biased and D2 is reverse biased. So D1 is going to conduct, so you get an output due to D1. During the negative half cycle, A is negative, B is positive. So here P is connected to negative, so D1 is reverse bias. Here P is connected to positive, so D2 is forward biased. So D1 doesn't conduct, D2 conducts, so you get an output due to D2. So during each half cycle, one of the diode conducts and you get an output here. So this is the output waveform of a full wave rectifier. So as you can see, during both half cycles, current flow through RL in the same direction. So you have a pulsating DC voltage obtained across the load resistance. Once again, this is not a clean DC. You can make it a clean DC by using a filter circuit. Now, what is the peak inverse voltage here? As I said, peak inverse voltage is the maximum possible voltage across a diode when it is reverse bias. Suppose Vm is the maximum possible voltage across half the secondary winding. Okay, so from here to here, the maximum possible voltage is Vm. From here to here, the maximum possible voltage is Vm. So the total secondary voltage is 2 Vm. So during the positive half cycle, D1 conducts and D2 doesn't conduct. As I said earlier, whenever some electrical component doesn't conduct, the entire voltage is going to drop across that component. So here the total voltage is 2 Vm, and during the positive half cycle, 2 Vm is going to drop across D2. During the negative half cycle, D2 conducts, D1 doesn't conduct. So the entire voltage 2 Vm is going to drop across D1. So the peak inverse voltage during a positive half cycle or negative half cycle is going to be 2 Vm. Now, what are the disadvantages of a full wave rectifier? First and foremost, it's difficult to locate the center tapping on the secondary winding of the transformer. That's a practical difficulty. Second one, as you can see from this scheme, each diode is going to utilize only half of the transformer's secondary voltage. The total voltage is 2 Vm, but each diode is going to utilize only half of it. So the output is going to be small. And finally, the diodes must have high peak inverse voltage. Only then you will have maximum efficiency. Even though it has so many disadvantages, clearly it is much more efficient compared to a full wave rectifier. So in the next class, we will derive an expression for efficiency of a full wave rectifier, and from the values you can note that the efficiency of a full wave rectifier is almost twice as that of a half wave rectifier. So with this, we will complete today's lecture. Thank you.